Good day, everyone. This is Rhoda P. Buong discussing the topic on seismic and electrical methods. In this video, I will be talking about three different methods, which are seismic, resistivity, and electromagnetic methods. The Earth's upper crust is composed of many layers of rocks and minerals that all have different properties such as hardness, density, and porosity. The placement of these layers gives clues as to the likelihood of finding mineral, hydrocarbon, and or hot rock reserves nested within them. This is a method of exploring the Earth's crust using artificially generated waves. Just like how doctors use waves to look inside the human body without the need for surgery, seismic analysis essentially generates an ultrasound image of the Earth. So how does this work? It starts with the generation of seismic waves. Seismic waves are typically generated by a controlled source, which could be a weight dropped on the ground, explosives, or specialized vibration device. The goal is to create a disturbance that produces waves capable of penetrating the earth. The second one is to propagate seismic wave. Seismic wave travels through the earth, penetrating different layers and reflecting back to the surface at interfaces where there are changes in subsurface properties such as rock types or geological structures. The third one is to record the seismic waves. Seismic waves are recorded by sensors, which are strategically placed on the Earth's surface or in boreholes. These sensors detect ground motion caused by the seismic waves passing through the subsurface. Seismic method works by sending acoustic energy waves created from a sound source through these layers. Typically, there are two methods for producing sound waves. First is by using vibroseis, and the other one is by explosive detonation, also known as thumper or a shaker unit. It is a large hydraulic drum that is fitted to a special truck. The operator stops the truck at the location where they would like to generate a signal and uses vibrosi to ram the ground, thus creating a series of sound waves, source waves. Microphones called geophones that have been specially placed in an array around the survey area pick up the reflected sound waves and record that data to a digital medium for later computer analysis. Sometimes, instead of using vibroseis, explorers will use an explosive like dynamite to create the source wave. Explosives are detonated, and an acoustic wave travels through the ground and is detected by an array of geophones that have been previously arranged. Because scientists know how long it takes for sound waves to travel through and bounce back from different types of rock and minerals, careful interpretation of seismic data can give them detailed cross-sectional and three-dimensional graphics of the subsurface of a surveyed area. This can help them find mineral, hydrocarbon, and hot rock resource deposits. The changes in properties between different rocks can cause reflection and or reflection or refraction of sounds. Seismic refraction occurs when waves change direction due to variations in subsurface velocity, while seismic reflection occurs when seismic waves encounter a boundary between two layers with different acoustic properties. For the data processing and imaging, seismic data undergoes extensive processing to enhance signal quality, remove noise, and convert it into a meaningful representation of the subsurface. Advanced imaging techniques such as seismic tomography and migration are employed to create detailed three-dimensional models. For the interpretation, geoscientists interpret the processed seismic images to identify geological structures such as faults and folds and stratigraphic layers. This interpretation provides valuable information for applications like resource exploration, environmental studies, studies and geological method. Next one is the applications of seismic methods, which includes environmental engineering studies, geothermal resource exploration, natural hazard assessment, and mineral explorations. Some applications also includes oil and gas exploration, groundwater exploration, carbon capture and storage, reservoir monitoring, and tectonic and earthquake research. Moving on to the resistivity method. This method is based on the principle that the distribution of electrical potential in the ground around a current carrying electrode depends on the electrical resistivities and distribution of the surrounding soils and the rocks. Resistivity is the electrical resistance of a conductor of unit cross-sectional area and unit length. It is useful in comparing various materials on the basis of their ability to conduct electric currents. High resistivity designates poor conductors. So how does this principle of resistivity apply in geophysical investigation? There is resistivity of rocks and soils, which varies within a wide range. Resistivity is the fundamental physical property of the metal in the wire. Resistivity is the property which we are trying to measure with resistivity surveys. Since most of the principal rock-forming minerals are practically insulators, the resistivity of rocks and soils is determined by the amount of conducting mineral constituents and the content of mineralized water in the pores. Most rocks and soils conduct an electric current only because they contain water. The widely differing resistivity values of the various types of impregnating water can cause variations in the resistivity of rocks. In the resistivity method, an electric current is introduced into the ground by means of two current electrodes, and the potential difference between two potential electrodes is measured. After conducting the surveys, geologists analyze the data with the resistivity scale for waters and rocks. If geologists record or obtain data with less than 10 ohm meters, they are dealing with either a very clay-rich formation or a formation that has salty water in it, or both. Most aquifers are in the range of 10 to 500 ohm meters, but they can be higher. For example, in cemented gravels. When the resistivity exceeds about 1000 ohm meter, they are generally in bedrock with little chance of productive aquifers with the exception of some fractures. Normally, it is not possible to measure resistivities above 10,000 ohm meters. The resistivity method is based on the fact that any subsurface variation in conductivity alters the pattern of current flow in the ground and therefore changes the distribution of electric potential at the surface. Since the electric resistivity of such factors as superficial deposits and bedrock differ from each other, the resistivity method may be used in the detection and to give their approximate thicknesses, relative positions, and depth. Electrical resistivity is a widely used geophysical method for environmental site management. Real-world geophysical surveys don't provide magical or perfect vision of the Earth's subsurface, but instead provide images that can be blurry and imperfect yet still useful. For the electromagnetic method, this method detects the electrical properties of the subsurface by inducing electromagnetic energy within the subsurface and measuring the response of Earth materials. Primary field is produced by a natural current source or an alternating current artificial source, and this field spreads out in space above and below the grounds, inducing currents in subsurface conductors, while secondary fields are produced by the current that distort the primary field. The secondary field induced in the subsurface conductor fades gradually when a transient primary field is switched off, fading being slower in media of higher conductivity. The electromagnetic energy is introduced into the ground by inductive coupling produced by passing an alternating current through a coil. The receiver also detects its signal by induction. The conductivity meter is carried along transverse lines across a site and can produce a direct continuous readout. Hence, surveys can be carried out quickly for electromagnetic method. Very low frequency is the most widely used fixed source method operating on a single frequency, making use of powerful radio transmitters. The interpretation of VLF data generally is qualitative, and it frequently is used for reconnaissance work. The method is well suited to detecting near vertical contracts and fracture zones. Another method for electromagnetic is the ground probing radar method, based on the transmission of pulsed electromagnetic waves in the frequency range 1 to 1000 MHz. In this method, the travel times of the waves reflected from subsurface interface are recorded as they arrive at the surface and the depth on interface. Ground probing radars have been used for a variety of purposes in geotechnical engineering. For example, the detection of fractures and faults in rock masses, the location of subsurface voids, and the delineation of contaminated zones. That's the end of my presentation where I discussed three methods of seismic and electrical methods. Thank you.